How do you feed a crew of astronauts on a 10-year journey through the absolute void of empty space? When Earth is nothing more than a pale blue dot lost in the cosmic dark, traditional agriculture becomes a fatal impossibility. The logistics of survival require us to abandon everything we know about food. Starvation is the silent mathematical killer of deep space exploration. Long before cosmic radiation or engine failure can claim a crew, the simple depletion of calories will seal their doom. But NASA has quietly developed a bizarre, almost unbelievable solution that sounds like pure science fiction. Farming in space is a beautiful lie. Greenhouses on spacecraft are wildly inefficient, consuming precious volume, water, and power while delivering minimal caloric yield. That is why NASA is not looking at soil and seeds. They are turning to advanced physics, thermodynamics, and extreme microbiology. A trip to Mars takes 7 grueling months. A journey to the icy moons of Jupiter takes 7 years. You simply cannot pack enough freeze-dried ice cream or military MREs for that kind of voyage. Food expires, essential vitamins degrade, and every extra pound of cargo costs thousands of dollars to launch. To survive deep space, NASA is bypassing traditional farming entirely. They are engineering systems to literally print edible, nutrient-dense food out of thin air, human breath, and metabolic waste. This is the story of how humanity will feed its interstellar pioneers using the laws of physics. Welcome back to Weapon Science. I am Ethan Walker. Today we are dissecting the extreme biochemistry and engineering behind deep space food synthesis. We will explore how closed-loop life support systems turn recycled carbon dioxide into delicious, life-saving meals for our journey to the stars. Imagine breathing out carbon dioxide and having that very breath captured, processed, and served back to you as a perfectly textured protein bar. It sounds impossible, but the physics of mass conservation proves that everything we need to survive is already inside the spacecraft. But before we can build this ultimate biological recycling system, we must understand the brutal physical constraints that make traditional supply chains completely useless. We must face the unforgiving reality of the rocket equation and the sheer mass of human survival. Every mission to deep space begins with a math problem. It is called the Tsiolkovsky rocket equation, and it dictates that the more mass you want to launch, the exponentially more fuel you must carry. This creates a vicious cycle where your rocket quickly becomes too heavy to leave the ground. To sustain a crew of 6 on a 3-year mission to Mars using traditional food, you would need to launch over 12,000 pounds of supplies. When you factor in the fuel required to push that mass out of Earth's orbit, the launch vehicle's required size and cost skyrocket into impossibility. This is known as the mass penalty. For interstellar missions lasting decades, packing food is mathematically equivalent to suicide. Every gram of weight dedicated to cargo is a gram of weight stolen from radiation shielding, scientific equipment, or life-saving thruster propellant. Furthermore, traditional packaging is heavy. Even lightweight aluminum and plastic pouches add up when you are talking about thousands of meals. In the cold calculus of space travel, dead weight is the enemy, and traditional food preservation is nothing but dead weight. Even if we could solve the weight problem with advanced propulsion like nuclear thermal rockets, we would still face a fundamental physical barrier. Food is not static. It is a complex biological structure that begins to degrade the moment it is packaged, regardless of how well it is sealed. On Earth, we rely on a continuous agricultural cycle to replenish our nutrients. But on a spacecraft, you are operating in a closed system with no external inputs. If your food supply degrades, there is no grocery store, no fertile soil, and no second chances. The math of survival is absolute. This mass penalty forces us to rethink the entire concept of a payload. Instead of carrying the finished product food, we must carry the machinery of production. But that machinery must be incredibly lightweight, highly efficient, and capable of operating continuously for years without failure. Every watt of power consumed by this food synthesis system must be accounted for. In deep space, solar energy fades to almost nothing, meaning we must rely on nuclear reactors. The efficiency of converting electrical energy into chemical energy and then into food is the ultimate metric. If the conversion efficiency is too low, the reactor must be larger, which increases the mass of the spacecraft, triggering the rocket equation penalty once again. It is a delicate, interconnected web of physics where every decimal point can mean the difference between life and death. This is why NASA's Advanced Concepts team is obsessed with efficiency. They are searching for the absolute limits of thermodynamic conversion. And as we will see, the solution they found bypasses the inefficient process of photosynthesis entirely, targeting the molecular level. But mass is only half the battle. The other, more insidious threat is time. Even if we could launch tons of food, that food would slowly become nutritionally useless. Cosmic radiation and simple chemical decay destroy vital nutrients long before the expiration date on the package. In deep space, high energy galactic cosmic rays and solar particle events constantly bombard the spacecraft. These particles easily penetrate standard food packaging, ionizing the delicate organic molecules inside and breaking down essential vitamins like thiamine, vitamin C, and vitamin B12. Within 24 months, standard military MREs and freeze dried space meals become nutritionally void. An astronaut eating this food would feel full, but would slowly die of scurvy, beriberi, or other severe nutritional deficiencies. Their bodies would waste away while their stomachs were full. This biological decay is a fundamental law of chemistry. Organic molecules are held together by relatively weak covalent bonds. Ionizing radiation has more than enough energy to shatter these bonds, transforming life-sustaining vitamins into useless or even toxic chemical compounds. To combat this, current missions on the International Space Station rely on regular resupply missions to deliver fresh food and vitamins. But once we leave Earth's orbit and head toward Mars or the outer solar system, there are no resupply ships. We are entirely on our own. This means we must synthesize these delicate vitamins in real time, on demand. We cannot store them. We must grow them. This requirement shifts the problem from food preservation to continuous biochemical manufacturing, transforming the spacecraft into a flying pharmaceutical factory. The challenge of synthesizing vitamins in real time is immense. It requires precise control over chemical reactions at a microscopic scale. Traditional chemical synthesis often requires harsh solvents and extreme temperatures, which are highly dangerous in a closed spacecraft environment. This is why biological synthesis is so attractive. Nature has already spent billions of years evolving microscopic machines enzymes that can synthesize complex vitamins at room temperature and in water. By harnessing these biological machines, we can create vitamins safely and efficiently. But how do we feed these biological machines? We cannot carry bags of sugar or nutrient broth to feed our vitamin-producing microbes, as that would bring us back to the mass penalty problem. The microbes themselves must be fed using the waste products of the crew. This realization leads us directly to the core concept of deep space survival, the closed-loop life support system. Nothing can be wasted. Every atom must be recycled. Your breath, your sweat, and your waste must become the raw materials for your next meal. The laws of physics are absolute, and the first law of thermodynamics states that matter cannot be created or destroyed. In a sealed spacecraft, every single atom of carbon, hydrogen, oxygen, and nitrogen that leaves Earth remains on that spacecraft throughout the entire journey. Currently, the International Space Station loops its water and oxygen with incredible efficiency. Over 90% of astronauts' sweat, urine, and breath moisture is reclaimed, purified, and turned back into drinking water. It is a triumph of mechanical and chemical engineering, but the carbon loop remains broken. Every day, astronauts exhale about 2 pounds of carbon dioxide. On the ISS, this CO2 is scrubbed from the air and vented into space as waste. This is a massive loss of valuable carbon, the fundamental building block of all organic life and food. To close this loop, NASA is developing systems to capture this exhaled carbon and combine it with hydrogen to create organic compounds. By reclaiming this carbon, we can transform the spacecraft from a waste-generating machine into a perfectly balanced, self-sustaining ecosystem. This is the essence of the Sabatier reactor, which is currently used on the ISS to combine CO2 and hydrogen to produce methane and water. But methane is a gas that we cannot eat. To close the food loop, we need a way to turn that carbon into complex proteins and carbohydrates. Traditional farming does this using plants, which use sunlight to convert carbon dioxide and water into sugars through photosynthesis. But as we established, plants are incredibly inefficient. They require massive amounts of space, soil, and light, and they waste most of their energy growing in edible roots and stems. We need a system that is far more direct. We need to cut out the middleman, the plant, and convert carbon dioxide directly into edible biomass. This requires a process that operates at near-perfect thermodynamic efficiency, utilizing every single watt of electrical power to build chemical bonds. This thermodynamic efficiency is the holy grail of space life support. In a closed system, any energy lost as heat is waste that must be radiated away into space, which requires large, heavy radiators. Efficiency is not just about saving power, it is about reducing the thermal load of the ship. By using electricity to drive chemical and biological synthesis directly, we can minimize these thermal losses. We can create a system that operates at a fraction of the size and weight of a greenhouse while producing many times more food. This is the promise of molecular food synthesis. To achieve this, NASA is turning to some of the oldest and most resilient organisms on Earth, organisms that do not need sunlight, soil, or fresh air to survive, organisms that can feed directly on electricity, gas, and waste. It is time to meet the microfarms of the future. Enter hydrogenotrophic bacteria. These remarkable single-celled organisms belong to a class of microbes that can survive in the most extreme environments on Earth, from deep hydrothermal vents to toxic volcanic springs. They do not need light. Instead, they eat hydrogen and carbon dioxide. In a spacecraft bioreactor, these bacteria are fed a steady diet of carbon dioxide captured from the crew's breath and hydrogen gas produced by splitting water. The bacteria use this energy to grow and multiply at an astonishing rate, doubling their mass in a matter of hours. The resulting bacterial biomass is incredibly rich in nutrients. By weight, these microbes are over 70% pure protein, packed with all the essential amino acids, healthy lipids, and vitamins that a human body needs to survive. It is the ultimate superfood, grown in a bottle. This process is hundreds of times more efficient than growing plants. While soy crops convert less than 1% of solar energy into edible protein, hydrogenotrophic bacteria can achieve an energy-to-protein conversion efficiency of over 50%. It is a thermodynamic revolution. To keep these microbes happy, the bioreactor must maintain a perfect, delicate balance of temperature, pH, and gas concentrations. This is handled by advanced AI control systems that constantly monitor the bioreactor's vitals, adjusting the gas flow to maximize growth rates. The hydrogen gas required is generated by water electrolysis, a process that is already standard on the ISS. By using excess electrical power from the ship's reactor to split water, we create both the oxygen the crew breathes and the hydrogen the bacteria eat. The loop is elegant and complete. But eating a wet, pale paste of bacterial biomass every day for 10 years is not a viable option. It would lead to psychological breakdown, a phenomenon known as menu fatigue. Humans do not just eat for nutrients, we eat for pleasure, texture, and cultural connection. Menu fatigue is a recognized psychological danger in long-duration spaceflight. If astronauts find their food repulsive, they will eat less, lose weight, and suffer from cognitive decline. To prevent this, we must transform this raw bacterial paste into something that looks, smells, and tastes like real food. This is where the engineering of food structure comes into play. We must take the raw proteins and lipids produced by our microbes and reconstruct them layer by layer into familiar textures and flavors. We must become molecular culinary architects. This transformation requires a combination of food science, materials engineering, and advanced manufacturing. And the primary tool for this culinary revolution is a technology that has already transformed manufacturing on Earth: three-dimensional printing. 3D food printing is not just a gimmick, it is a sophisticated method of structural engineering. By extruding synthetic protein filaments in precise microscopic patterns, we can mimic the complex cellular texture of real meat, creating the illusion of muscle fibers and fat marbling. To do this, the raw bacterial paste is first dried, purified, and processed into edible inks. These inks are then loaded into the printer, which uses precise temperature and pressure controls to extrude the material through microscopic nozzles, building the food layer by layer. By adjusting the density and pattern of the printed layers, the printer can create foods with different textures, from tender steaks that require chewing to soft, melt-in-your-mouth pastries. This variety is critical for satisfying the human brain's desire for sensory diversity. Flavor is another critical variable. The raw bacterial protein has a very neutral, slightly nutty flavor. To make it appetizing, we must inject natural or synthesized flavor compounds, such as amino acids, sugars, and organic acids, into the printing process. These flavor compounds can be designed to react when heated, mimicking the Maillard reaction, the chemical reaction between amino acids, and reducing sugars that gives brown food its desirable flavor. This means our synthetic steaks will actually smell and taste like they are cooking. This Maillard reaction is a complex cascade of chemical reactions that produces hundreds of different flavor compounds. By mastering this chemistry, we can create food that is not just edible, but genuinely delicious, satisfying the deepest culinary desires of the crew. The potential of this technology is limitless. We can print personalized meals tailored to each astronaut's specific nutritional needs. If an astronaut is running low on iron or calcium, the printer can automatically adjust the recipe, injecting the perfect dose of nutrients into their next meal. This level of personalization is impossible with traditional prepackaged food. It turns the kitchen into an extension of the medical bay, proactively managing the crew's health and performance through precise, customized nutrition. It is the ultimate form of preventative medicine. But to feed these printers, we need a steady supply of more than just protein paste. We need carbohydrates, fats, and other organic molecules. And while bacteria are great at producing protein, they are less efficient at producing sugars. For that, we need a different kind of chemistry. We need a way to bypass biology entirely for certain steps, using pure electrochemistry to build organic molecules from scratch. This leads us to one of the most exciting areas of NASA research: the development of the artificial leaf and electrocatalysis. The artificial leaf is a device that mimics the core function of photosynthesis, but without the biological limitations of plants. It uses advanced electrocatalysts to capture carbon dioxide and split water, using electricity to forge carbon-carbon bonds and create simple organic molecules like acetate. Acetate is a simple two-carbon molecule that is incredibly versatile. It can be used directly as a food source by certain yeast strains, or it can be used as a chemical precursor to build more complex sugars, fats, and even bioplastics for 3D printing packaging. By using electrocatalysis, we can achieve carbon to organic conversion efficiencies that are 10 times higher than natural photosynthesis. This means we can produce the raw materials for food using a fraction of the power and space required by even the most advanced hydroponic greenhouse. This process can operate in complete and utter darkness. Unlike plants, which require massive amounts of light energy from power-hungry LEDs, the artificial leaf runs on pure electricity. This makes it ideal for deep space missions, where solar energy is non-existent. The heart of this system is the catalyst. NASA is developing nanostructured catalysts made of copper, gold, and other metals that can selectively drive specific chemical reactions, ensuring that we produce only the organic molecules we want with zero waste or toxic byproducts. These catalysts are incredibly durable, capable of operating for thousands of hours without degrading. This reliability is critical for deep space missions, where replacing a worn-out catalyst is not an option. The chemistry must be as robust as the physics. By combining electrocatalysis with biological synthesis, we can create a hybrid system that is far more powerful than either technology alone. We use electrochemistry to build the simple building blocks and then use microbes to assemble those blocks into complex, delicious foods. This hybrid approach represents the absolute state-of-the-art in space life support. It is a perfect fusion of physics, chemistry, and biology, operating in a closed loop to sustain human life in the most hostile environments imaginable. It is the ultimate survival machine. But even with perfect technology, we must never forget the human element. Survival is not just about calories and nutrients, it is about the mind. And to keep a crew sane during a 10-year journey through the dark, we must address the psychological factors of eating. For humans, food is deeply tied to comfort, memory, and social bonding. The act of sharing a meal, of preparing food, and of experiencing different textures and aromas is vital for maintaining morale and mental stability during periods of extreme isolation. This is why NASA is not just designing automated food dispensers, they are actively creating systems that allow astronauts to participate in the cooking process. By giving the crew control over the shape, texture, and flavor of their printed meals, we can provide a crucial sense of agency. The simple act of customizing a meal can break the monotony of space life, providing a creative outlet and a connection to Earth. It turns a sterile, automated task into a comforting ritual, helping to maintain sanity during the long, silent months in deep space. Furthermore, the sensory experience of food, its aroma, its color, and its texture plays a major role in digestion and nutrient absorption. If food is unappealing, the body actually absorbs fewer nutrients from it. Making food delicious is not a luxury. It is a biological requirement. By using microencapsulated flavor compounds, we can create foods that release bursts of flavor as they are chewed, mimicking the complex sensory experience of eating fresh, natural ingredients. This attention to detail is what will keep our astronauts healthy and happy. This holistic approach to food design, combining extreme physics with deep psychology, is what makes NASA's food synthesis program so revolutionary. It is a complete reimagining of the human relationship with nutrition designed for the ultimate test of survival. But the impact of this technology will not be limited to deep space. The very same systems we are developing to feed astronauts on their way to Mars could also solve some of the greatest challenges we face right here on Earth, transforming global agriculture forever. On Earth, traditional agriculture is under immense strain. Climate change, water scarcity, and soil degradation are threatening global food security, while our growing population demands more protein than ever before. We are running out of land and resources to feed ourselves. By applying the physics of deep space food synthesis on Earth, we can decouple food production from land and weather. We can build modular, vertical food factories in the middle of deserts, crowded cities, or disaster zones, producing fresh, nutritious food with zero environmental impact. These factories would use a fraction of the water and land of traditional farms while producing no runoff or greenhouse gases. They could turn carbon dioxide captured directly from the atmosphere into high-quality protein, helping to reverse climate change while ending global famine. This is the true power of space exploration. By solving the extreme challenges of surviving in the void, we develop the very technologies needed to save our home planet. The physics of deep space food synthesis is not just about reaching the stars, it is about protecting the Earth. As we push deeper into the cosmos, our survival will depend on our ability to master these closed-loop systems. By transforming waste into life and electricity into food, we will finally break free from the cradle of Earth and become a truly multiplanetary species. Thank you for watching Weapon Science. If you want to explore more deep dives into the physics of survival and advanced space engineering, make sure to subscribe and hit that like button. Comment below, what is the one food you would miss most in deep space? Until next time, I am Ethan Walker.